Again, everyone, it's wonderful to have you here to another one of our more in-depth technical presentations. And I must thank Quan, who has been running these for us for about 2 years now, and he's been doing a very good job. So thank you, Quan, for that. And welcome to everybody here today. I see so far we've got 18 participants, but I think actually that'll probably increase as we go on. Well, it gives me great pleasure to welcome someone from overseas. This is a very unusual thing, Trung, so we're absolutely delighted. And the fact that you had to get up very early this morning because you're speaking to us from the west coast of the US. And I'm delighted to welcome an esteemed researcher from Adobe Research. So I'll pass over to Quan to introduce you. And on behalf of everyone here, and particularly the CeADAR Center, Trung, we want to thank you for being here today.
Yeah, thank you, Edward. So everyone, welcome to the online tech talk series of CeADAR. So I first introduce the format of the talk, and we will have a speaker do the presentation for like 40 to 45 minutes. And then, the presentation will be recorded, and after it, we will turn off the recording and you can ask the speaker questions. And for the talk today, we have Trung Bùi, who is a senior research scientist and a research manager at Adobe Research. He has done a lot of work in Dialog and in natural language processing. And he has experience in developing products which serve millions of users. So I think his talk will be very interesting. Okay, Trung, I hand it over to you to your presentation.
Thank you, Quan, and good afternoon, everyone. It's my great pleasure to meet you and share my work and research with you today. The title of my talk is Toward Multimodal Dialog for Conversational Image Editing. And so here is the outline of my talk. So I will cover two main parts. The first part is mainly the research on conversational image, ongoing research on conversational image editing, and the presentation based mainly on a paper we published at CeADAR 2018, and also cover the ongoing work after this paper. The second talk is also related, but more into the line of neural network and deep learning, also apply to dialogue and related problem as Adobe with context-dependent additive recurrent neural net, which is also a new set of models we developed at Adobe, and this work was also published at ACO 2018. It is a joint work with my former interns, colleagues, and professor from Australia. And I will, in the second part, I will cover use cases we apply at Adobe to different problems like language modeling, question answering, and end-to-end dialogue. So let me go to the first part, conversational image editing. So, I think that nowadays there are a lot of people use capture photo because thanks to the popularity of mobile devices, smartphone, it's very easy to capture images. But after that, so then people often need to edit the image. And when we talk about image editing, we mean that improving certain characteristics of the image, such as brightness, contrast. And as you know, there are tool, software tool can help users to do that, such as Adobe Photoshop or Microsoft Photo and other as well. So here it couple of example of usually when we have an image, we can express our intention of editing an image through natural language, such as either want to add cloud to the sky or make the image from color to black and white. But basically, image editing is very time consuming and require artistic creativity, patience, and experimentation. And also user may not be fully aware of the features supported by given image editing tool. For example, if you have already used Photoshop, you see that there are a lot of features. So it is very hard for the beginners to know all the features and to apply it effectively. And in some situations, there are particular, for example, here two situations. That's the first one that user may not be sure about what changes to perform on given image. Usually the user have a vague request, like for example, make this horse look less grumpy. Another problem that user also may not know an abstract level that what changes they want, but unaware precise image editing step require, such as remove an object from the photo. Currently, there are web services for image editing. For example, for beginner, they can post their photo to online services and ask professional photo editor to help them to edit it. There are a couple of web services available, such as Reddit, Photoshop, Recurrent, or Zoop. But usually, user will pop up an abstract request to embed and edit to edit an image. So for example, here an example from the Reddit Photoshop request, like I love this photo from our last holiday. Can someone please remove my ex from this photo? I am on the right one. I am the one on the right. Rather than, for example, when user uses software, they need to do very concrete multi-step instruction, like select the body on the left, replace the region with the trunk on the bottom, using replacement tool, and so on. So therefore, we, in order to have beginners that can edit photos, images easily, we develop a framework of conversational image editing. This will address the limitation of the online web services for image editing. For example, in the forum-like setup of web services, the user cannot request changes or provide feedback in real time. Usually, the user post an overflow and wait for the professional to edit and to put back the results. And also, editor also cannot ask for clarifications or provide suggestions as the image editing is being performed. And our ultimate goal is to build a dialogue system with such capability, meaning to support user to edit image in real time with an expert image editor. So in order to do so, we can perform very popular approach in developing dialogue system, conversational system, is that we conduct a wizard-of-all experiment. So in play of the computer, we have two people setting in two different locations, and one assumes the role of the wizard or the assistant, and the other is user. And user can see the screen of the wizard and can provide comment requests And let me show here the example of what we collected.
Head down.
All right.
A little bit higher to like the black frame. And from the bottom, that wheel is absolutely useless. So let's like get rid of that. A little more. That's good.
Okay.
So do you hear audio okay? What?
Yes, you do. Yes.
Okay, good. Yeah. So based on, we collected the data from mostly internal user within Adobe, and then after we collected the data, then also when we analyze the data, we also realize that there are incrementality in the interaction between the user, and therefore, in order to develop a dialog system to support this use case, we need to take into account the incremental interaction processing between the user. As you know, in popular dialog system nowadays, such as Amazon Alexa, Apple Siri, usually the system waits for the user to finish the request and then run up behind the scene. There's some speech recognition, language understanding, and speech output sequentially and provide feedback to the user. But we argue that if we can take account the incremental processing, meaning that allow different modules like speech recognition, language understanding, or speech output running in parallel, we can shorten the processing time to give the feedback to the user, as illustrated in this case. Actually, the typical example, if we don't allow incremental processing, then we have the timeline for different components. So in the last, in the right mode part of the figure here. But if we even perform partial incremental or full incremental, we can significantly shorten the time for the system to respond back to the user. So it also actually apply perfectly in our scale of conversational image editing because it requires a lot of fine-grained changes, and the editor also need to understand the user utterances incrementally, word by word in real time. So here's another example of the dialogue that we collected.
Whatever was blue, it just made it bluer. Is that what you did?
Exactly. Yep.
Can you try it a little more? Like even bluer? Let's see. Oh, that's cool. All right. Maybe not quite that much there. That's right there. It's good.
Yeah. So for this talk, we set up the wizardable experiment that I described over Skype, and we allow screen share feature enable on wizard screen. And in this setting, we use Adobe Lightroom image editing tool and set up with 28 users, 2 wizards. Each user will perform like 4 to 6 images, no time constraint, and photograph are chosen from the sample of public data set with so popular categories such as animal, citizen, food, nature, landscape, indoor scene. And also we have option for the user to bring their own photos as well. And here's the data that we collected. It contains about 130 dialogue, but I think one special feature that you can see here is that the average length number of utterances of both wizards and user very long compared to typical dialogue, let's say a book, a restaurant, or hotel. So it's usually about 10 times longer. And given that having this dialogue is typical to develop a system, then we need to do labeling annotation. One important label in developing dialogue system is dialogue arc annotation. Identify the user utterance and do perform utterance segmentation, and for each segmentation assign a dialogue arcs. By the way, the dialogue arc it's defined as the main intent the user want to communicate with the system. For example, such as asking a question, or reply, or respond, confirmation, and so on. And for this task, so here we have here a list of dialogue arc label so that emit edit requests, request recommendation, request feedback, asking emit location, suggestion, and so on and so forth. And we also analyze and have a statistics of all the dialogue arcs used in our collected data. And not surprising that there are two popular dialogue arcs. It's emit edit request new and emit edit request update. It also shows that it have very incremental interactive interaction between the user and the wizards. And this is an example of the utterances that we transcribe from the speech from the corpus, and also we assign the tag to the dialogue in this example. So also when we perform dialogue arc annotation, we also realize that in order to have the agreement, we also have two expert annotator to annotate the same dialogue session, and we computed the Cohen kappa, and in this case, the agreement is reasonable for this domain. And here is the example of the annotated data for our corpus. So we have it a bit more complex cases when we have a long utterance with multiple commands, and then basically we split them into different segments so that each segment is associated or assigned a particular dialogue arc. And then in addition to our dialogue arc, we also label like action, attribute, location, object, value. The reason why we need those detailed labels because this attribute are needed in order to form an API call to the image editing applications. So after we have the label data, then we also start building a machine learning model to detect the dialogue arcs, and we investigate different various dialogue arc detection models that popular in the literature, such as using neural network-based model, LSTM, CNN, along with traditional models such as naive-Bayes, CIF, random forest, and so on. And by running through this model, we found out that surprisingly, the CNN model trained on word embedding and CeADAR perform the best. Because our intuition and hypothesis that because it is more or less input sequence input text, so we expected that USTM perform best in this task, but it turned out that CNN perform much better, and also LSTM model perform not so good, even worse than basic baseline such as random forest models. So another part that I mentioned earlier, the incremental feature of this task. So this figure show the confidence level of different dialog arcs along the way when we start recognizing the dialog arc along the way that user starts talking to the system. What it means that at the beginning, for example, if user only say one word, then we have different confidence of different dialog arc candidates. But when we have more and more information of user, and then we see that the final candidate dialog arc in this case it image editing request new. And interestingly that in this example it shows that we can reliably recognize this dialog arc halfway user complete the command. We don't need to wait until user finish this request, but halfway we can already recognize the dialog arc associated with user input. And here it specifically how we calculate and identify the correct class, dialog arc class, given partial input from user. So in this example, as you can see here, we can save like one word from user input utterance and can reliably identify the class associated with this utterance. And then this figure shows overall the percentage of correct prediction and percentage of word saving for correct prediction at a function of confidence threshold. So you can see here that if we set confidence threshold like around 0.5, then we see that we can see it's the red line shows the percentage of word saving, and the blue lines shows the percentage of correct prediction. And this is more the detailed number of words, number of occurrences of dialog arcs, percentage of word saving, average word saving per utterance, and percentage of correct predictions. And so overall, for all dialog arcs, we saved like 1.7 words per utterance, and still maintain a reasonable percentage of correct prediction. There are some utterances that we can save more, like image edit requests. We can save more words, but some we can say less. For example, like request response yes no, because by nature this utterance is often short already, 1 or 2 words. Okay, so in summary, we introduce kind of a conversational image editing framework with a novel real-world application domain which combines language and vision. And this domain is very well suited for the research problem of incremental dialogue processing. we compare different models for incremental dialog arc detection and found that CNN performed best on this. And also we calculated the impact of varying confidence thresholds on classification accuracy and word saving. And through this experiment, we show that incremental intent processing or dialog arc detection could be more efficient for user and save time in accomplishing the task. So there are follow-up work after this, which I can go quickly, especially it's relevant to the part of how to implement the system prototype based on the data we collected, and to be developed system multimodal dialog system prototype that incorporated with our image editing product. Another, in addition to recognizing the dialog arc in a dialog system, that another very important part in developing that system is to develop a dialog policy or to learn policy, how the system respond to the user. For example, given a request, the system can decide whether to edit the image or maybe ask for clarification first, and so on and so forth. And for this task, and from the data, we build a simplified model with only 5 basic image editing operation. And for each operation, that also attributes associated with operation in order to carry out image editing actions. And then we build a model based on reinforcement learning Markov decision process framework, which we have the policy, state update, and also a simulated user model trained on the collected data. And we also implemented an image editing engine in order to train the dialog policy for this framework. So this is a kind of high-level overview of the framework, a mathematical framework that we use. Basically, we formulated at a Markov decision process where we have state, it's a dialog state, action is system action, or wizard or assistant action, and we have state transition property, so the user state, and also we have reward signal to reflect the quality of the dialogue. And the goal, when we formulate at a Markov decision process, and the goal is to maximize the reward over the whole dialogue sessions. And then this is typically the part of how we run the simulation between user simulator and the dialogue policy in order to generate the episodes of interaction. Also the reason why we use user simulator, because in order to train a dialog policy based on Markov decision process, it requires a lot of sample data, and that it's typical approach that we use the data, human collected data, to build a user simulator, with it mimic the behavior of the user. And then after that, use that user simulator to train the dialog policy models. So for this, we also did the experiment setting. We use, I think one part I mentioned, it is why it's a multimodal dialog, because that also image part, processing parts. That's why we need to develop a kind of vision engine. And also we develop a Photoshop emulator, and we sample images from a public data set, MS Coco, for training set, and set the goal for the user, like usually the user will open an image, perform various different modification, and just close it. and we set a maximum number of turns, 30. Also, this is also based on the statistic we collected from the human image editing dialog, and we evaluate several metrics such as average number of turn goal completed, and then the result we got so far is that we compare with different competing baseline such as rule-based, also rule-based, and also now with the framework that we use here, it's DQN, it's a deep Q network. And from this, we also see clear trend that when the semantic error rate increase, then the machine learning policy perform better than the rule-based, and rule-based model degrade quickly. And also, usually after we conducted experiment testing the model with simulated user, we also conducted experiment with real user. So basically, in this talk, we tested with about 10 grade students, and each person complete 2 dialogue for each policy, and total number of dialogue with 20 dialogues. And also, in this case, we also show that interesting that both rule-based and machine learning approach has the same success rate, but with machine learning, we reduce the number of turns significantly from on average 3.9 turns compared to rule-based with 5.8 turns. So another observation from the experiment that we see that the turn number related mostly to the user behavior. Some prefer use only text longer, and some use both text and gesture shorter. And also, all the values cases are incorrect understanding of the image adjustment. And also it suggests that we need a better natural language understanding model. Yeah, so therefore, I think a follow-up work based on this, that we continue to annotate out our data set in the framework of what we call dialogue state tracking. What different from dialogue act recognition and language understanding we saw before compared to dialogue state tracking is that dialogue state tracking, we take into account the whole history of the dialogue in order to predict what is user intent and entities. And also in our framework, unlike conventional dialogue, let's say for restaurant booking, hotel booking, in it we need to formulate at a multi-frame problem, because each image auditing operation is equivalent to a frame formulation. And to give you an example, what it is frame, for example, in a restaurant booking, it only needs to formulate at one frame problem. Usually, and when you book a restaurant or you want to find a restaurant, you need to provide a couple of properties such as type of food, location, price range, and so on and so forth. But in our framework, each image editing operation already require a set of properties. So that's why we formulate at a multi-frame dialogue system. And then here it's the example of annotation, both from language understanding and frame annotation for the dialogue in our framework. Yeah, so here you can see that through this short conversation, it already 3 frames involved. the first one, it complete by itself, like one image editing operation, like Brighton the yellow dot. The second part involves one frame, but it unfolds into different interaction with user, continue to update the image like incrementally. And the third one is also a frame by itself with a complete image editing operation. And this is the example of the annotated data that we collected. Yeah, so based on that, we built various internal prototypes with our system. But here, let me show you an example of the initial prototype that we developed. Yeah.
How can I help you?
I'd like to reframe this picture.
Cropping.
Make it square.
1-to-1 aspect.
Now flip it sideways.
Flip horizontally.
No, go back.
Undo.
I like it.
Committing changes.
Post to Facebook.
Yeah.
Goodbye.
Goodbye.
Yeah. So this is the only prototype that we developed on an iOS app for Photoshop Fix. And currently, I think one limitation of this app is that it's not you cannot perform object editing specifically on the photo. So that's why we are developing prototypes on directly on the Photoshop, which allow us to perform a lot of complex interaction through with the image. So now let me move to the second part. By the way, how much time do I have left, Quân?
I think maybe 6 minutes. So
okay.
I have to go through it fast.
Okay. So then I go to quickly for this start. I think the second part is more about new neural network model we developed for different other tasks at Adobe. I can go quickly. So the background here is you see that this is a formula of popular LSTM model, and also another simplified model called Recurrent Additive Neural Network. Basically, the key difference here from an LSTM to RAN, it simplified in computation of the first part and the final part of the hidden node into the model. And based on that, we came up with the idea that can we even simplify further the model like recurrent additive network model. And actually what we did is that we add the context to the model, and then and then with this context, actually it allows us to capture the long-term dependency between the in the sequence model that we are applying, and later it will be clear. And then we perform several improvements. The first improvement is that we remove the dependency of the current state with the previous hidden state. I think if we can do that and maintain the performance, then I think it significantly simplifies the training time and inference time of the LSTM model. And the second improvement is that we also replace the current approximate hidden with simplified input embedding. And after that, then we applied it to 3 different problems. The first one is the end-to-end dialog problem, which we take the input, it's a sequence of token, and sequence of token here, meaning that dialog history, current, address, and then try to predict what is the probability of the candidate next address in a dialog flow. And the second model we apply it for language model, and what we call it contextual language model. By the way, language model, I think it had application into various NLP problem, for example, speech recognition, and also downstream NLP tasks. And in this, we use the same contextual additive RNN block, but to develop the model that take into account. So here, in the type language model, that we have the current sentence, and also the next sentence, and also the context we use is the dialog classes of the previous sentence given the current sentence. And we apply this for another target question answering. So basically, at the time we replace the LSTM model by our CA-RNN component and maintain the same architecture. What it called I1 architecture. It is the best state-of-the-art model for question answering. And based on that, we got, I think, very good significant results. So for example, for end-to-end dialog at the time, by simply replacing this CA-RNN component, we got significant improvement when we perform on public dialog dataset like Baby from Facebook, and also Frame dataset from Microsoft. And here is an example of when we compare CA-RNN to the baseline. So basically, as you can see here, it compared to other model, it can take very long information from several turns in the dialog context in order to derive what is the next action in this dialog applications. So another application we apply here for contextual language modeling, and for this we also perform tests on 2 public datasets, popular dataset, Pentibank and Sweetbot, and we also have significant improvement compared to state-of-the-art model at the time. So by the way, here the metric is perplexity, meaning it's smaller is better. And we apply this, and this the result for question answering. So we compare to the model using LSTM and other state-of-the-art model, and also we have better in both metric in this question answering application. So here, so the example of the I1 model using our CA-RNN compared to LSTM. So it also shows that, so in the typical LSTM model, you see that given a question, only the first answer candidate are more or less relevant to the question. But in our model, it shows that even top 3 answers also are highly relevant to the question as well. So that is the model, and I want to, given that shortage of time, I can quickly go a couple of applications that we are developing within Adobe using the model we developed. So the first is document question answering. problem. So it is in this. So usually, let's say that if you open a document either from the web or Acrobat, and you ask a question, then based on the model that we can identify what is the relevant sentence from the document read to the question, and did it actually what you we take here that a document from the web, and then we perform a couple of questions here, and we see that the result is also quite reasonable. It is still an ongoing work, and some of the work related to that work actually we put in a release, of Acrobat release this year, in May this year. For the language modeling problem, we also apply here in CAP what we call domain-specific speech recognition, and we apply for the same data that we collected before image editing requests, and we benchmark it with popular speech recognition API here from Google, Microsoft, and others, and we also see that with the new custom language model, we significantly achieve better accuracy performance compared to other popular common large-scale speech framework. So in summary, so the CANM framework, I think it's very computational efficiency because we remove the dependency between private hidden state and propose very much simpler model, and also by introducing the context, high-level context information, it also reduce the training time. So for some part here, we can reduce like 40% of training time. Yeah. So and this is the end of my talk. Thanks for your attention.